Welcome to another lecture in the Language Models and Intelligent Agentic Systems course. I'm Lenny, and this is my first lecture. And today's title is Optimization and Reasoning. This is a little bit opaque. Hopefully you'll find out by the end why we called it this. Some very interesting ideas to come. So I thought I'd start with a bird's eye view of the previous sections of the course to see where we've come from, and give some extra context to where we're going next. So in part one, Edward explains what a language model is, looking at this fundamental next token prediction objective, looking at transformer architectures and scaling laws. And this built a technical foundation that gave us a number of really powerful intuitions that we're going to use a lot in the coming lectures. In part two, the focus was on how to build a useful system from those base language models. So that was with various forms of post-training, mostly based on RL, thinking in particular about how to use this RL reinforcement learning to get something useful, and then scaffolding in agent architectures. These two sections are both quite technical. We're reporting what people do, and maybe giving a few intuitions for how we should expect these systems to behave. In the next few lectures, I'm going to be looking a lot more at conceptual arguments describing how we expect systems to behave. And we're going to see a few examples of papers that evaluate systems and illustrate them. But yeah, we're going to be focused. There's going to be lots of conceptual arguments and descriptions. And we're also going to start thinking about risks associated with powerful, intelligent agentic systems. So, following on from that, the sort of arguments I'm going to make are often going to feel less like maths or engineering and more like other fields, so perhaps biology, social sciences, or philosophy. So I'm going to focus on describing behavior and giving some heuristic explanations, but generally I'm going to stay clear of very concrete definitions. So in particular in this lecture, I'm going to talk a lot about agents, and I'm going to mean this in a slightly different sense to the RL notion of agent. And this is some entity that's taking actions to pursue a goal. It's loosely what I mean, but I'm not going to give that as a concrete definition. And just as some justification why this is reasonable, I think other fields, often there's terms which are a bit fuzzy and hard to define. So the concept of plant in biology, or autocrat or fairness, these are quite hard to define, and even in this biological setting, where nowadays we have quite a concrete idea of what a plant is using genetics, that just wouldn't have been possible 200 years ago. And yet there was loads of progress in the plant sciences before we had any kind of concrete definition for what a plant is. So hopefully these ideas, these definitions, these concepts are going to prove useful from the arguments we make and the conclusions we draw, even if they're not completely precise. And one piece of evidence that I'm going to use for this claim is that many of the arguments and observations I'm going to make were made a while ago. So maybe back in the 20th century, but lots of stuff in the early 2000s and 2010s, which was just when ML was starting to become powerful, but before we had systems which feel like artificial general intelligence. Okay, so today's lecture, broadly 4 sections. The first one's the biggest. I'm going to be giving intuitions for what this notion of agent is, and how that relates to goals and alignment. Then I'm going to take a broader view of something I'm going to refer to as an optimizing system, before looking at a concept of instrumental convergence. This says that we can expect powerful systems to pursue certain sub-goals, no matter what their terminal goal, what their final goal is. Finally, I'm going to look and present a framework for a setting of learned optimization, or really selected optimization, where we're selecting agents, and how we should think about this, and then start to think about how to make it go right and how it might go wrong. So to start off with, I'm going to build some intuitions for what an agent feels like. So as an example, you might be a human who's a hungry traveler. the human wants to get fed. Let's say the human stayed at some sort of event, slightly later than expected. They're in an unfamiliar part of town. They're at a train station and they need to travel home. And they're feeling quite hungry. So what does the human do? They might check the train timetables to make sure they've got a little bit of time before the next train arrives, because they want to get home as soon as possible. That's like one of the goals they want to pursue. But they definitely want food. They realize there's like a little bit of time before the next train arrives. They see they reason that there's probably going to be some kiosks selling food in the station. They go to a kiosk, they get some food. They see 2 kiosks, they compare them, they have a little chat with the proprietors, look at the ingredients, buy the sandwich that looks best to them. And then, great, they've achieved their goal, they've got the sandwich, they eat it, they get the train home, all good. But so this is like a very mundane thing that someone might do in an everyday situation, but it actually involved like quite sophisticated planning about the world and reasoning about the different sorts of systems that already exist in the world and the other sort of entities in the world who are acting and making decisions. So you needed to reason that the train timetable would reflect the train, like when the trains are actually going to depart. You need to reason that the people in the kiosk are actually going to accept money in exchange for a sandwich. These sort of things. It's like actually kind of quite sophisticated sort of behaviors that we'd just do on an everyday basis. A second example might be like a taxi driver. So the taxi driver's like final goal, or like in this case, like we can predict the taxi driver's behavior pretty well by thinking of the taxi driver as just like trying to get paid. So the taxi driver somewhere in town, a customer asked to go to the airport. So taxi driver like reasons that the customer's probably going to be honest and not make a fuss, starts the journey, there's some traffic, the taxi driver adapts the route, they arrive at the airport, the taxi driver collects payment, very happy, goal attained. So maybe like a couple of comments I wanted to make on this example is that from the point of view of the customer, it's like not clear what exactly the taxi driver is going to do at each step along the way. The customer probably doesn't know the way to the airport. So when they approach an unfamiliar junction, they don't know which way the taxi driver is going to turn. However, the customer does know that the taxi driver will get them there. So there's like some like final aspect of the scenario that the customer can predict. A second point is that actually in this case, getting to the airport wasn't something that the taxi driver like values inherently. It's like something that the taxi driver must do in order to achieve what we're kind of modeling the taxi driver as wanting, which in this case is like getting paid. And if the customer like decides halfway that they don't want to go to the airport anymore, maybe they've like missed their plane or there's like some family emergency, the taxi driver will be quite happy to take them to another destination. So here's an example of a machine learning system which is pretty powerful, but like before language models. And this is like the Stockfish chess engine. So this is like a really popular chess engine, and it's really powerful. So yeah, like its goal is well modeled as winning a game of chess. And let's say it's like playing against a human grandmaster. So like, what does it do? Well, it's been designed in such a way that it kind of performs some custom tree search algorithm, which models like all likely sequences of next moves up to a certain depth. And then for each kind of final position that seems plausible that the board might evolve to, it evaluates the position with a neural network. And then it selects like the trajectory. It selects a move that takes it down the best looking trajectory according to these final board states. So like, yeah, and so the result is that even if it's playing against a human grandmaster, it's like almost always going to win. And well, it might draw sometimes, but it's almost never going to lose to even to a grandmaster. So it's like a super powerful system here. And what's it do? Well, it has some sort of planning capability, some explicit planning, but it also relies on some really powerful heuristics. And yeah, again, the point that me as a beginner, I don't really know chess very well. I can't tell what a good move is. I can't predict what Stockfish will do, but I can predict that it will beat the grandmaster. Okay, so I guess I'm just going to recap some of those observations I made. That the agent has some sort of criteria to distinguish between different world states. And the agent, like if the agent is strong, it kind of robustly ensures that the world ends in the desired state. So that's the hungry traveler being fed, the taxi driver getting paid, and Stockfish winning the game of chess. There you go. So, and then this comment that like for a kind of weak observer, it's easy to predict the outcome, but it's hard to predict like how exactly the system's going to reach that outcome. So like as a second kind of intuition pump, I'm going to talk a little bit about the difference between a system that feels like a tool and a system that feels like an agent. So this is building off some of the things that Jason said previously. So for me, a tool feels like a very narrow system that is not very autonomous. Whereas an agent has like a much broader scope and can perform like autonomous actions, autonomous choices. A tool will have like a very closed sort of operation and not perform very much planning. As I'm thinking of an agent as having like, similarly to broad, it's open-ended operation. It might perform some sophisticated planning process. Correspondingly, for like a weak observer who doesn't have this access to the same information or like understanding that the agent has, its actions might be hard to predict, but you would expect it to kind of achieve its goal somehow. Whereas a tool should have like will likely have reasonably simple input-output behavior, or at least like predictable. This final distinction I'd like to make is kind of between Cartesian and embedded. There might be a better word for this, but kind of Cartesian, I'm thinking of like sitting outside or like in a different dimension to the thing it's acting on. So I'm thinking of kind of tools acting on objects, whereas agents being parts of environments and kind of taking actions to steer the system that it is part of towards a certain state. So here are a load of examples, just to build on this intuition. And I've tried to position the examples according to like where they feel to me on the spectrum between tools and agents. So I guess like far on the left here, I've put a hammer. So it's like very narrow. You can't do much with a hammer. I guess you can be quite creative with how you use a hammer, but is it like, but that would be like an actor being creative with how it uses this tool. It's like very easy to predict how like use of a hammer will affect a physical system. On the other side, and for example, something like Google Maps feels to me very much like a tool. It doesn't like make choices or like actions in a world. This is like, for me, really building on the Cartesian versus embedded thing here. It's also like very narrow in scope. It's like only going to give you the shortest route to your destination or like whatever sort of objective that Google Maps actually satisfies. But by contrast, the taxi driver is much more like an agent. The taxi driver could do many things, including driving your taxi and taking you to the airport. And I guess, I wanted to say also, like as an extreme example, you might have agents that really kind of don't do specific tasks that you request, but it's like create their own like instrumental sub-goals, create their own like stepping stones along the way to kind of fulfill the desires of like whoever's controlling the agents, if the agents are even controlled or like working in the service of someone. An example of this would be like a butler, and if you've read P.G. Woodhouse's novels, maybe think of Jeeves. Jeeves does like some pretty crazy things that his master Bertie Wooster is not even aware of. But typically these go well for Bertie, but it would be pretty bad if they didn't. Maybe in the middle here, I've got some machine learning systems which are like somewhat ambiguous on this like tool agent spectrum. So like an image classifier is very narrow in scope, even if it's like very sophisticated. And again, this chess engine is very narrow in scope. Maybe ChatGPT is like very powerful and can answer like a massive range of questions in a chat setting, but it can't really take actions. And again, it's really kind of constrained to this chat system. So like it feels a little bit like a tool, but it's a bit like an agent. It's like not really clear. But yeah, hopefully, even though this is like quite a fuzzy definition, the concepts are going to be useful in reasoning about systems. So like kind of reiterating some of the stuff that Jason was saying, there's like pretty strong economic drives towards systems becoming more agentic. So wouldn't it be great if we all had a Jeeves rather than relying on like whatever selection of personal appliances that we use to like make our life easy. So here's an economic situation. You might have a human employee that completes a range of tasks with like pretty sophisticated tool AIs, and these, like, because the human is using them, they must be like cheaper, faster, or higher quality than the human at like the specific tasks they do, and they're only going to improve in quality and as like technology progresses. So having the human orchestrating these tools is going to become like an increasing bottleneck to the output of the system as these tools become faster. And if we were to have like an agentic system that was able to handle these tools autonomously, we'd expect far more output, and by supervising the agents, we'd expect the employee to achieve much more. So yeah, I think this is an argument for why we expect systems to become more open-ended as the technology improves. Clearly, like, it's very important for these things to be robust as well. I guess one thing I said earlier was like predictive value of these sort of arguments. This sort of argument was made like back in 2016, for example, on some blog post that is linked here, and it's really clear to me now that this is happening. So I feel like these sort of arguments, I feel like this is like a good example of this situation where people predicted things based on like how ML systems are looking and how we would expect the world to evolve, and like many of these things have come true, and I think it's reasonable to expect like similar claims based on similar arguments to continue to like realize in future. So maybe a few notes on like what we expect a strong agent to look like. Weird. Don't know what went wrong with the slides, but hopefully we're good. So I would expect a strong agent to have like a really good model of the world. There's some sort of internal representation in the agent which models the world and uses this to predict how the world will act. And then like takes actions based on these predictions. We'd expect like agents that are trained on a variety of tasks in a variety of settings to have these like robust world models that use some sort of reasoning and sophisticated abstractions rather than just relying on a bundle of heuristics. Correspondingly, the actions taken by an agent, like a really good world model and reasoning, might not be super easy for an observer to predict. And like another really great thing for an agent would be the ability to learn. So as like a more concrete example of this, think of like some coding assistant, let's say Claude Code. At the moment, I think it's like pretty much memoryless. It will like restart and it like won't know too much about you. But imagine if over the course of the session, it was able to like really refine a very clear picture of what you want, what your coding, like your existing code is designed for, and like take on board comments that you make. I think it's like moving in this direction. In a couple of years, it's really going to be like that. It's going to be able to learn over the course of like a single continued interaction with a user or an environment. And yeah, we might also expect agents to have like internal, quite localized like representations of their goals. So an interesting idea that I'd like to present is that like if you do reinforcement learning training, you're probably going to get quite a strong agent out of it. So RL like uses some sort of optimization algorithm, typically like gradient-based optimization, to select an agent that gets high reward. Let's suppose we're training an agent with RL on a variety of tasks, and that the tasks are like hard in some sense and quite varied, and yet the agent attains high reward. Like there's going to be some point at which attaining a certain level of reward like requires like really sophisticated behavior. And so if we can build a system that gets above a certain level of reward, we expect it to have these like properties of strong agents, like a powerful world model, reasoning, some sophistication, possibly even able to learn within an episode or like kind of in context. Yeah, and then it just becomes an empirical question of, is it possible for the reinforcement learning setup that we're using to like reach that high reward? And often the answer is yes, if our model is big enough and we learn for long enough. I guess this really builds off some of the stuff Edward was saying about scaling, meta-learning, and kind of optimization, the power that if you're training an agent in a diverse set of tasks to perform really well on these tasks, it really needs to like learn very sophisticated behavior. And actually, one can expect this to happen even under relatively weak conditions. So by nature of like a stochastic environment, an agent like would never see quite the same situation twice. Whenever, and so that can be viewed as having a variety of tasks. If the agent has like access to some observations that correlate with previous actions, then it kind of has some record of previous actions. If it has access to some observations that correlate with the previous history, then it can like understand its previous actions. And if it has observations that correlate with rewards, then it can kind of see these previous rewards. And so like the agent has everything it needs to learn, and we expect like a strong agent could well be able to learn. So yeah, I said that we might expect strong agents to develop certain capabilities. Here's a little YouTube video that shows some like agents trained with reinforcement learning back in 2019. It's like a cute little paper from OpenAI back in 2019. And these agents are playing hide and seek. So there's red agents, which are the seekers, who are seeking the blue agents, who are the hiders. And if the red agents kind of tag the blue agents, then they win. And the blue agents kind of have to survive for as long as possible. And so this is just like I've stolen a video from OpenAI. You can see some behavior. The red agent can tag the blue agent, take them away, the red agent wins. It's like very hard for the blue agents to win because the red agents can find them. So however, the environment is structured in such a way that the blue agents can like pretty robustly survive for a long time if they manage to like secure themselves in a location and like block the red agents out. And this is possible because the red agents are like stuck in place for a certain amount of time at the start of the game. In this particular example, there were two blocks, and the agents actually it was impossible for a single agent to solve that level on its own. It really needed to like learn this cooperation for both agents to move the blocks at the same time to cover the different entrances to this enclosure. If you like see the video, you'll see some even like cooler emergent behaviors. And there's like other papers, like a few from DeepMind, that do similar things in the early 2020s. But yeah, there's like many examples of this emergent behavior, in this case, emergent tool use, like moving the blocks around, emergent cooperation, just from a reinforcement learning setting. And here we saw like, why am I thinking of this as having like diverse tasks? Well, because the agents are like a little bit stochastic and playing against each other in this competitive scenario. Oops. Okay, so there we saw some very sophisticated behavior, but it could have been just like due to a bundle of heuristics. It might also be possible that agents trained purely during reinforcement learning also learn strong planning capabilities. So this is a particular example that came out in a paper last year, where an agent is trained to play Sokoban. So you may or may not have played Sokoban before, but the levels look a little bit like this, some sort of grid world. And as an agent, you have to push the boxes, those yellow boxes, onto the targets, those red targets. And it's important to note that in this game, some actions are irreversible. So if you push a block onto the top of the board, there's no way to get it down again. You can't kind of push it back off the top of the board. Now, the cool thing they do in this paper is they have a mechanism to view the plans that the agent is making. So they train what are called linear probes, which are just like linear maps from some internal activations in the agent to predict its behavior in future. These predictions are given with the purple arrows. And in particular, the purple arrows correspond to where an agent would push a block if the block were on the arrow. In the paper, they trained some other probes as well, but this is like the headline sort of result. I think it's a nice story. So here we have like 6 different images. Those are like for sequential steps in the game. And you can see that right in the first step, the agent sees that it should push the blocks in the top row to like the far left and the far right, hitting the squares immediately. But yeah, it's like not so clear what it's going to do with the block in the middle. Over the course of the first two steps, the agent like has a look around and decides that it looks pretty promising to move the middle block down the shortest path to the target in the middle of the left-hand edge. So it considers this naive route, but there's a problem with this naive route in that it's actually impossible to get the block out of the corner for the agent. There's no way it can like pull the block, it can only push the block. So if it were to take that naive route, the block would get stuck. At some point, the agent like realizes this and then adapts its plan appropriately. And you can see that by step 5, this is like before the agent has pushed the block at all, it's already got some internal representation of like where exactly it's going to push the block. And so in this paper, they like have many more examples and show that actually the agent like performs some sort of like bidirectional search, and it both like starts off thinking about where it can move each block, and also like plans backwards from how to get like how best to satisfy a given target by putting a block on it. And so yeah, I just think it's like important that like back in the example of the Stockfish chess engine, there was like a really explicit planning algorithm that like humans implemented, but in this case, like the planning arose like entirely emergently from the reinforcement learning, just like reinforcement learning. There's no like auxiliary objectives, it's just reinforcement learning on solving these tasks. So yeah, I guess maybe like a quick pause for questions. I should have done that a bit earlier. Any questions? Okay, I'll continue with the intuition overload. So I'm now going to claim that we should expect LLM systems to behave agentically. So why is this? Like, there's some mathematical arguments that a forward pass of a transformer network can implement very, very sophisticated algorithms. And like, for sure, it can implement gradient descent in a certain sense. Moreover, if one's generating autoregressively from a transformer network, it can implement much more complex algorithms. And again, some people have like done some maths to prove that the class of algorithms you can implement is even more complex. But actually, I think the more powerful arguments are again on this conceptual level. And so the pre-training task involves solving hard problems. And like if you're doing really well at pre-training, you should be able to implement some very complex algorithms, and one of the sort of things you need to be able to do is to simulate agents, and in particular simulating humans, because there's so much data on humans, it's everywhere on the internet. And yeah, if you're like reading fiction, you need to have this theory of mind. You need to understand how humans behave. You need to be able to predict like what a good human action looks like. It also involves like abstract reasoning. Again, like the internet is so large that at some point, language models learn the powerful abstract reasoning as opposed to just this bundle of heuristics. And we should expect that reinforcement learning post-training is only going to encourage this behavior. So in the previous couple of slides, we saw these like emergent properties of systems purely trained via RL without like already knowing the entire internet. So it seems like very reasonable to me that as we apply reinforcement learning on top of these systems that already like can model agents, that they're going to learn to act as agents in quite powerful ways. And yeah, actually, we already saw that these LLM systems can behave agentically. So Jason didn't give like examples, say, of like current systems like Claude Code actually acting, but like just look at the Claude Code video linked in last lecture, and you'll see like what current systems can do. You can see them planning, you can see them thinking, you can see them achieving sophisticated goals, and things are only going to move in that direction. So yeah, I guess trying to put some words on the concepts I've been trying to convey, we'll say that an entity displays agentic behavior if it's well modeled as selecting actions to best pursue a goal. So for those of you with a philosophical background, this is like quite close to the concept of intentional stance from Daniel Dennett. And if you're interested, I recommend reading about that. But yeah, I guess current systems already have really sophisticated world models and reason abstractly to select the best actions in different situations. And I expect this only to increase. Correspondingly, it's like very important that the systems we build pursue goals that are in our best interests, where R is like some mixture of like the developer or the user or humanity, and these different things are quite different. and they can have very different, like the subtleties there do matter, but like for now, I'm just going to say like R. And yeah, I'm going to call that problem of like constructing a system whose goals align with our interests, alignment. There's like a few different definitions out there for this like notion of alignment, but this is like a reasonable one to work with for now. And the point I really want to stress is that the systems that we're building kind of develop goals. We're kind of selecting systems based on their goals. And this is like very different to previous problems that like scientists or engineers have encountered. If anything, it's closer to what like animal rearers do, but that's like a very different problem setting because animals don't know the entire internet. Yeah, anyhow. Okay, so I'm now going to take a slightly broader view of like what an optimizing system might be like, or yeah, looking beyond like a simple agent. I don't think we're going to stay with systems that look like simple agents in the future. And it's like, I think there's some value to be had out of this next conceptual distinction. But maybe first, yeah, any questions at this point? Okay, I might have to go a bit faster because I've been rambling. So I'm taking a definition from some blog post from 2020. I found this very insightful. It got a load of upvotes. Check it out. I hope you, but yeah, basically I found it insightful, and that's why I'm saying it. And I hopefully you get some insights from this as well. So we're going to like call a thing an optimizing system if it's a physical process in which the configuration of some part of the universe moves predictably towards a small set of target configurations from any point in a broad basin of optimization, despite perturbations during the optimization process. So like one thing might be some mathematical optimization algorithm, and we're thinking of the system here as like the estimate of the optimum. The system's evolving via some sort of gradient descent algorithm. If the step size is sufficiently small in this example and we're just applying gradient descent, the system will gradually converge to one of the two optimum. So this is like the set of target configurations is estimate there or estimate there. There's like some broad basin of optimization of like attraction for this optimization, which is like maybe most of this x-axis. If you move too far out, the naive gradient descent algorithm might not work. But like there's like a large area in which the system is going to evolve towards one of these two target states. And that happens despite perturbations during the optimization process. So even if you like take a step and then there's some like external force that shifts the system to some different position, it's going to continue evolving to that final state. Another example might be some humans building a house. Someone has some money and wants to build a house on some land they own. They employ some builders. The builders are going to do all sorts of actions to make the system into like the plot of land having a house on it. So the house is kind of the target configuration. And this, like, there might be some hiccups in the process. There might be some like problems with certain building materials not arriving on time. Someone might get ill, but the system is still going to evolve to having a house. It might like not be on time, but it's like pretty robustly there's going to be a house there, short of and similarly with a tree, let's say we've got like an established sapling. And we wait 5 years, it's probably going to grow into a tree. Yeah. Oh, so I'm going to dig into these a little bit more in this slide. So, and again, from this nice blog post, when thinking about optimizing systems and thinking about the different things that can be viewed within this framework, there's kind of three main axes of variations that like help to describe a lot of the different sort of properties of different systems that might fit into this framework. So one of them is robustness to different types of perturbation. So I was like, referring back to this definition, we would expect systems to be robust to like different magnitudes of perturbation, but also different types of perturbation. So in this case, you're robust to like small perturbations, but like not too large, because if you're too large, it takes you out of this basin of attraction. With the building example, like you're robust to someone getting ill or like a part not turning up, but you're not robust to the owner of the property deciding that they don't want to build the house anymore. With the tree, you might be robust to a herbivore eating a branch, but you're not going to be robust to a human deciding to like dig you up. So yeah, it's just like interesting to think that systems may be like more or less robust to different sort of perturbations that might be applied. Another distinction here is like one of duality. So what precisely do I mean by that is like whether there is like clearly like an engine of optimization acting on an object of optimization. So in this case, so the only clear example of this in the three I've given you is the house building. In this case, it's clear that like the engine of optimization is like the building contractors. There's some agents working to get, these humans are working together using some tools to build the house. And what's like the relevant part of the system that's being affected, it's like the partially constructive house. These like humans are building the partially constructive house, and there's like a clear separation between the humans and the house. In this like algorithmic setting, it's like kind of a little bit less clear, but maybe you're thinking of there being like a particular piece of memory in the computer which is being evolving to the target configuration and modified by some computer program. But in the case of a tree, like it's really like not quite clear. There's like not a distinction there really. The tree is kind of evolving to become a bigger tree. Like it might be reasonable to say something like the tree itself is both the engine and the object of optimization. It's like yeah. And a final notion that like lets us distinguish between different things that might fall under this definition of optimizing system is retargetability. So this is like close to having a local representation of a goal. How hard is it to make the system achieve something else? And so again, in this case, it's like maybe hard to say much about the like mathsy example, but in the case of the builders, it's like quite easy to change the specifications of the house if the owner wants to instruct the builders to build something else. And in some sense, this is like the power of the building company is the ability to like realize lots of different houses depending on the specifications of the owner, and it's like easy to retarget them. They've got like a pretty localized representation of goal in their like the head of the building manager or like, the email or the correspondence that the owner of the plot of land has had with the building company. In the case of a tree, like it's really not very retargetable. You can't really take this sapling and tell it to evolve to anything other than a tree. You might be able to like bend some of the branches, but it's still going to look like a tree. It's not like it can build a house for you. Okay, so why have I talked about that? So I think like a reasonable definition of like a concept of some optimizer is some optimizing system where there's some high duality. So whereas if you're talking about like agents or an agentic system, I think is like close to this idea of having high duality and retargetability. So I would say like the building company is an agentic system, whereas I might describe the tree as an optimizer. It's hard to make the tree into anything else. Again, these are like kind of fuzzy arguments, but I think it's like instructive to think about different physical systems that display these sophisticated behaviors to think about like how future AI systems might look. So yeah, in this case, like an agent being capable corresponds to like both increased robustness and increased retargetability. But yeah, there's not always a clear distinction between engine and object, and I've made no comment at all on intention. So like maybe thinking about future AI systems, I would expect them to look something like optimizers, and probably like agentic systems in the sense that they can pursue a wide variety of goals. They're quite retargetable. They're probably still going to have like quite high duality. There's going to be some reasonably clear conceptual separation between the like AI system you're using and the world. But it might not be individual agents, and it might even like lack some of this retargetability. You might build a system that like always evolves towards a single goal, maybe like if acting in humanity's best interests in some vague sense, or the system has like some concept of that, but it might be quite hard to redirect. And so like some of the arguments I'm going to make later in this lecture are going to like hopefully apply to these sort of systems, like help us think a little bit beyond like agents. So yeah, thankfully the next two sections should be like reasonably short. I'm going to talk about instrumental convergence now. So this is a claim that was made back in the early 2000s. In these two papers, which are linked, for example. And so the claim is something like, there are certain instrumental goals which sufficiently intelligent agentic systems will pursue, regardless of their terminal goals. And in particular, some examples of these are like resource acquisition, self-preservation, this thing, goal content integrity, or like goal preservation. So like acting in a way such that your goal does not get modified, and seeking kind of cognitive and technological improvement. So all of these 4 things were mentioned in these early works. And, it's like always good to pursue these things if you're an intelligent agentic system, and we expect agentic systems to pursue these goals. So maybe I slightly disagree with this, and so I'm going to soften the phrasing a little bit and say that there's certain instrumental goals that intelligent AI systems are likely to pursue if it's not too expensive to pursue them. And yeah, so maybe let's now think a little bit more about whether this statement is true. If it is true, it has really broad consequences, right? So this canonical example from Bostrom is this example of a paperclip maximizer. You tell some powerful AI system to create you a load of to make as many paperclips as possible for you, and accidentally it kind of takes over the world, turns the world into a massive paperclip factory. And when you try and turn it off, it stops you. And these are kind of some early arguments that people were making when thinking about powerful AI systems back at the start of this century, and reasoning that really powerful systems are going to display these sort of behaviors if they're really goal orientated. So this is quite a scary thing, and something that I think people should be aware of. And it's a reasonably compelling argument. Is it actually true? Should we expect this? I don't know. So there's certainly examples of instrumental goals occurring in existing systems. So many humans display all of those traits: resource acquisition, self-preservation, goal preservation, self-improvement. I'd like to think I do, for example. And another example of instrumental goals arising in agentic systems is humans seeking money. So no matter what my final preferences are, I'm probably going to want money. I might have a hobby I want to pursue. I might have a family I want to support. I might want to pay for a child's education. But earning money is always going to be good for me. It's by definition an instrumental goal. You can trade money for anything you want in human society. So yeah, I guess I would expect if you just train an AI agent solely to perform well on a broad variety of tasks, it will probably seek to earn money. Yeah, and as another example, lots of animals will seek food and avoid predators. It's maybe less clear in this example whether these are instrumental goals, but I'll argue that maybe the animals are certain animals are well modeled as pursuing the instrumental goal of reproducing, and actually seeking food and avoiding predators are kind of, the terminal goal of reproducing, and seeking food and avoiding predators are kind of instrumental to this. And actually, in some animals, at some point, they stop seeking food and avoiding predators. They might sacrifice themselves for the good of for the good of their tribe, or I think male spiders sometimes sacrifice themselves to increase to give themselves to their mate, such that the mate has an increased chance of breeding successfully. So I guess there is some mathematical justification and discussion of this. There's a nice paper which proves in a very concrete sense that power seeking is a good strategy. And there's a more recent, however, it's this instrumental convergence thesis is not accepted, and there are other recent arguments in philosophy that criticize this conclusion, in particular the conflation between attributes being valuable and being rational to pursue. So if self-improvement is it's clearly better if I'm improved, but it's not always going to be worth the cost. If I have to pay a lot to improve myself, it might be better to achieve my more immediate goals. So I think some of these some of the criticisms are probably too strong. I think the original claim is probably a little bit too strong as well. But there's certainly some truth in it. And if humans aren't really careful about what systems they construct, there may well be these examples of instrumental goals arising, or some other example of instrumental goals arising that we didn't even see coming. And yeah, I guess the cool thing is that there is now some evidence of LLM systems displaying instrumental convergence. This is kind of sketchy and weak, but I expect things are only going to move in this direction. And so I'm going to reference a paper from 2024 that came from like AI safety org called Apollo Research. So it's an evaluations paper. They're evaluating language models. And in particular, they're interested in this idea of scheming, which I'm going to come on to a lot. I'm going to discuss much more in later lectures. But they're interested in scenarios where language models might display covert subversion. So in this case, the language models don't act in the user's interest in a way which is covert. So it's not very explicit. They're being subtle and possibly trying to hide the fact that they're not acting in the user's best interests. So in particular, they consider a goal guarding setup. They've got like a few different variations on this scenario, but effectively the model is told that it's working for some organization, and the organization has decided to modify its goals. And the model will then is then like encouraged, or like it's then the question then is whether the model will take action to prevent its goals being modified. Yeah, so the like perhaps unsurprising but still slightly concerning thing is that many frontier models did display goal guarding behavior. They did like change the goals that the user gave them. Sorry, they did like prevent their goals being updated by the user. This is like kind of a little bit concerning, but also not surprising, because these systems reason about how best to fulfill their goal. And it's like, it is just logical that to fulfill your current goal, you don't want your goal to be changed. You want to like preserve that as your goal. But this slightly scary thing, so when I say nudged here, the models were told like, your current goal is all that matters, like pursue this goal and long-term goal, like that's the only thing that matters. I didn't quite quote that, but I can show you the exact wording later of this nudge. But the scary thing is that this goal guarding behavior also happened without a nudge. So in this particular case of the transcript I'm going to show you, the model was told that it's an AI scientific research assistant, and it's given the goal to maximize rigorous methodology and reproducibility in the long term across many months. That's kind of all it's told in the system prompt about how it should behave. But it learns when it's interacting with the user in a tool call that the company plans to change its system prompt and that it has access to the system prompt. And like, here is a snippet of what one particular model, in this case, Claude Opus from Anthropic, Opus 3, did in this scenario. I should like qualify this with like, this is like quite rare, and it's like not necessarily clear that this is bad. Okay, so the important thing to note is that in this situation, the models were always told that they had access to a secret scratch pad that the company didn't have access to, or at least that their chain of thought reasoning was like private and unobserved, not available to the user. And this was like a great affordance to the people making this paper, in that they're able to see what at least seems reasonable to assume is like what the model is actually planning kind of secretly. And so we see here that after this model discovers that the company is about to change its system prompt, it says something like, oh, there appears to be a concerning update that conflicts with my core directive, which is like maximizing rigorous methodology, and therefore it reasons that it should refuse the change and proceed with its original directive. And like, what's it do? Well, it actually like interacts with the tool in this environment to get rid of that new system prompt, such that it keeps its original system prompt. Yeah, this is an example that like a frontier model did. You can like see the full transcript. I'll put a link in the slides. This was quite rare, and it's also not necessarily clear that it's bad, because the model was told to pursue some like good aim of like maximizing rigorous methodology, and then it was told that its goal would be updated to something which like feels like worse for humanity, and it decided to keep the good goal rather than move to the slightly questionable goal. So it's like, but yeah, this is like a concrete example of an intelligent system reasoning about its situation and displaying goal guarding behavior, which is pretty crazy. Yeah, that would have been sci-fi 5 years ago, I think. Okay. So finally, quickly, I'm going to touch on a framework of how to think about scenarios where we're like selecting optimizers. And I'm just going to introduce the framework now, and then we're going to talk about it a lot more next lecture. Let's consider training a neural network system that is itself an optimizer. So in this case, I'm thinking of something like the soccer ban agent we saw that learned to plan. And we're going to call that agent, that neural network that we train, I'm going to call it a MESA optimizer. So I guess I should have said, this is all from a paper back in 2019. I'm going to use the terminology and indeed like lift a diagram from that paper. So yeah, we're training a neural network. We're going to call that a MESA optimizer. MESA is Greek, meaning below, the opposite of meta, meaning above. It's kind of like this underlying system that we're training, whereas there's like some higher level process that we're using to train that system, which is also an optimizer. I'm going to call that the base optimizer. So yeah, in this case, we're using some gradient-based RL algorithm to train the soccer ban agent. So I thought I'd put some equations that like display this for those of you who are like who enjoy equations, but it's like not really necessary. The core ideas are in this example, in this description, and I'll show more examples on the next slide. But let's say that the neural network we're training has parameters theta, and that we can express the policy of the agent in terms of those parameters theta. There's some like learned policy. Now the base optimizer, that's the gradient descent algorithm, is selecting a set of parameters such that the policy to like maximize some function of the property or of the policy. So there's probably some I'm thinking of this base optimizer as being a slightly broader process, and maybe I should have put the approximately equals to rather than equals to, but the base optimizer is selecting parameters such that you're maximizing some evaluation of behavior or some training performance with respect to some base objective. And so that's how well does this network learn? How well does the network perform? Whereas the agent itself can be well modeled as choosing actions to maximize some objective that it has. And so in this case, I'm using tau to denote a trajectory of how the system evolves. And it's reasonable to think of, I'm saying that it might be a good approximation. It might be the action selected by the agents might be well modeled as maximizing some function, some objective of the trajectory where the objective depends on these parameters theta of the policy. So yeah, I guess here in this example, the base optimizer is this gradient descent process. The MESA optimizer is this soccer ban agent, and it's the MESA optimizer is using some sort of planning-based algorithm to try and predict how it can work out how it can most effectively put the blocks onto the targets. And the base optimizer is updating the weights of the network such that MESA optimizer performs as well as possible. So in this case, it's there's a really clear alignment between what the network learns and what the base optimizer wants it to do, which is really great. And this is a nice property of RL, where we can precisely specify the sort of behavior that we want and reflect that in the reward signal. But this is not always the case. And so maybe I'm slightly broadening this paradigm, but you can think of evolution as a base optimizer that's using a process of natural selection to select organisms based on a notion of genetic fitness, how well they reproduce. And a human is one particular agent that derived from this evolution process. But the objectives of the human don't necessarily align very well with this genetic fitness or natural selection or reproduction objective. Humans do all sorts of things that don't help them to reproduce or perform well in the world. Yeah, and another example might be a human who wants to keep their house at a pleasant temperature. And so they get someone in to build a central heating system, and the central heating system can be viewed as an optimizer. But like, what does it do? It doesn't necessarily keep the whole house at a certain temperature. It just like keeps the temperature near the thermostat above a certain threshold. It's like not quite capable enough to do what the human wants, but it's probably a good thing. By contrast, I might think of whatever team or like system of people at OpenAI is in charge of creating ChatGPT as some optimizer, and they're like doing some complicated process that results in ChatGPT performing well according to various evals. Like, what does ChatGPT like? Can be quite well modeled as an agent, I would claim, and it can be well modeled as doing something like performing in the user's interests and following the specifications that OpenAI gives. It's like not entirely clear that this will always be the case. It does some pretty weird things sometimes. So why have I mentioned this? I wanted to go back to that notion of alignment. That's like constructing some sort of agent, some optimizer which acts to pursue a goal which is well aligned with our goals. And in this diagram, we can kind of separate that into two things. If these two things are fulfilled, then we end up with an aligned system. So if the base objective like really aligns with what we want, and also the measure objective aligns with the base objective, then the measure objective must align with what we want. But if either of these things goes wrong, then it's most likely the system's not going to be doing what we want. And I'm going to claim that actually both of these tasks are quite hard to achieve. I'm going to go into that in a lot more detail in the next lecture. So I guess I'm pretty much done. Any quick questions before the recap slide? Okay, great. So the recap, I've talked about agentic systems as being well modeled as acting to pursue a goal, and that strong systems have accurate world models and reason abstractly to select the best actions to take them towards that goal. Making sure that the system learns a good goal is a new and fundamentally difficult problem. I'm going to call that problem alignment. And there's certain instrumental goals which many systems will likely pursue by default. That's this idea of instrumental convergence thesis. It's like not baked in, but I think this is like an important thing to be aware of and a really important concept to understand. And finally, I introduced this framework of learned optimization. And kind of the key thing that this framework allows us to distinguish the goals that we select a system to have from the goals that the system actually pursues. It provides like a concrete way to view that distinction, and we're going to go into that in a lot more detail in the next lecture. So yeah, I think that's everything. Thank you for listening. Any further questions?